Hello, I am Harun from Imatic, the machinery company. Today we will introduce the 11-axis ring and bracelet processing machine that we operate with the Radonix control unit. We use 11 different servos on our machine. These are separated as X, Y, Z and C. The reason we say our machine has 11 axes is we use 11 servos for different features. These are what we call the X-axis, what we call the X1 axis, from here right and left. Our axis. Following that, when we say X2 axis, we have our axis here where we give the dome and radius movement. Then our X4 axis, from here, this is an axis that allows the bracelet's width to be fully automatically adjusted. Following that, the Z axis. Our Z1 axis. Each of these Z's is for a different feature. Our Z2 axis. And our Z3 axis, there is also our Z4 axis below. This is the axis that automatically adjusts the diameter on the machine when we change the diameter of our bracelet. We also have 3 C axes. One of them is C3.
The other one is C2.
Another one is our C1 axis, which we use automatically. It's over there. Our C axis that we use for tool changing. Finally, our third C axis, the one we use for tool changing. Our C1 axis. Our machine also has one Y axis, rotational axis. We attach our bracelet and wedding ring onto this axis.
Our machine has 11 axes. The first of these is the X1 axis. The X1 axis moves our machine block to the right and left in this way. Our second axis is X2. This is the axis that performs the bulge movement. It makes the machine perform the radius movement in this way. Our third axis is the Y-axis, rotary axis. Since this machine is 11, we do not have a Y2 axis. We have space here, but it is not present right now. Next, we have the Z axis, 4 of them, Z1, Z2, Z3. Each of these axes is for a different feature. We also have the Z4 axis below. This optimizes the machine's radius and diameter changes. We have 3 C axes as well. Among them the C3 axis, C2 axis, and we have the C1 axis, which we use for tool changing. And finally, our X4 axis. This is the axis that automatically adjusts the machine to the center when we directly change the width of our bracelet and ring.
Our machine has a home sensor for each axis. These inform us of the machine's positions. So when we home the machine, it resets itself at a specific point, and then we can instantly see where the machine is from here. From this moment, when we press this button, all our axes will home themselves in sequence. We can adjust their order ourselves from the back settings. We will show these in the upcoming sections. Now we will show the back settings part of our machine. Firstly, there is an active access feature in our machine. This means we can determine how many axes we will use the machine with. We can add or remove these as we wish. Following that, there are home sequences. So when we say home, there is a sequencing system for the machine, like let's C1 and C2 go first, then C3 and Z1 later. We can completely adjust these sequences ourselves. Afterwards, for home machine, we need to make adjustments in our inputs. That is from here, to which axis we will connect the number 1 input on our card. We choose after the home pin whichever axis we will use.
We put a comma.
We put a comma, and if we are going to use axis x1, we define it as x1. If x2, then x2. After writing this here, we need to press set. This number has now become our x1 sensor. Then we need to continue this as x-lux, x, and so on. What else is there? What else is there? We have outports, sensor pin already. These have something for safety purposes here. The thing, tool resetting. So when we say tool resetting, you need to know the tool length each time you take a tool from the tool changer. This sensor is used for that. We also have an emergency stop in the same way. Afterwards, we have our outports. In the outports, we activate things like spindles, valves, relays that we will use on the machine, meaning we determine what each one will do from here. So we can direct the outputs on the card as we wish. There is no restriction there. For example, we can make number 1 the spindle start. We can assign number 2 for coolant, for example. We can completely adapt this ourselves. We just need to configure it for each task we do. So from the link section here, we need to select what we will use it for and inform the machine. That's it. It's a simple matter. Now we will recognize the outputs in our system. They have adjustment systems. For example, the first output we have is the spindle. We have a tool changing spindle. This spindle can use 9 different tools at the same time. So we write the spindle's number, that is tool number 11. We put a comma in between. 12, 13, we can leave it at 15 if we want, or we can increase it up to 18 or 19. Our system allows up to 9, it gives the machine start to 9 tools from a single output. That is, it starts the spindle, then we have a second spindle. In this, for example, we have what we call a link. What do we do in the link? We say a spindle rotation tool, CWP pin, and write its number. So we activate number 2. In the same way, we can continue with number 3. So here 3, 4, 5, we can increase these according to the number of motors we use in our system. When we say clamp in, it opens and closes the tool chain system of our spindle here. That is, it activates the system that pneumatically releases and grabs the tool, which we refer to as clamp in. When we say tall pill, this refers to a tool we have on our piston. The moment I start this tool, the system automatically first retracts the piston, then it ensures the operation of the tool, for example, the operation of number 4 here, But first, the piston, which is connected to a valve, we call the toll pin. A command goes from the valve to our piston. Our scanner pin, this is a sensor we use as a surface scanning sensor. It fully activates its operation. These are also our tool change systems, which we call holders jack pin. So when the machine moves from number 11 to number 12, the system automatically opens the tool change cover. We have a safety sensor there. As soon as it detects the safety sensor, the machine can go and change the tool. Here we have what we call a toll height pin. We have a second system. Here we also have a sensor where we adjust the tool length. It activates the piston to which we connect this sensor. So when we tell the machine to take the tool length, the system directly engages this sensor, pulls the piston, and the machine can automatically take the tool length. Next, what we call brake pins. Suppose there are brake pins. These automatically deactivate the brakes of our brake motors when the system is turned on. We can also duplicate this in the same way from here. These pins extending downward are used to multiply an axis. So when we expand one x-axis to 4 axes, we determine through which I/O they will receive commands here. So as you might see, the moment I press X1 from the jog on the screen, it shows which I/O will be activated here. We can see it right across. For example, the x-axis is connected to number 32, X1 axis. Our control card has a test program made by the Radonix company. From here we can control all the IOs of the card. We can check if it is working, if the connections are made correctly, including the servos. We can control all of them from here. These are inputs, meaning whether the sensors are detecting or not, whether they are in the correct place. Here are our output puts. We can check from here whether the correct output is given to the correct motor. For example, the output connected to our third spindle is number 3. When we click here, our spindle rotates. It means we have connected it to the right place. We can perform the tests from here. For example, from the outputs, number 1 activates our spindle. As soon as we check it here, our spindle starts to turn. When we press it again, it turns off. For example, number 7 will pull the piston. Sensor we have our scanner piston. When we click on number 7, in this way both the piston is activated and our reader sensor. When our machine is ready to operate, there is an event we need to do. That is this. We need to load a parameter into our servos so that it can adapt and communicate in our program. We have a file here. This file was used by the Radonix company. It is already provided according to the servo CEO. If it's Panasonic, it's given as Panasonic. If it's Mitsubishi, as Mitsubishi. As soon as you load this file and say writing from here, when you say axis writing, your servo and control unit can communicate with each other and you can control it as you wish from here. Following that, what we call auto-tuning is done for the servo's power control, stopping and starting settings. That can vary completely mechanically. After setting up our machine and after making our servo and our software communicate with each other, we need to adjust the gear on our servos. That is what we call step adjustment. We do that from the settings section in our program. From the system and the axe section, our Z-axis, for example, since they are rotary axes that rotate a full 360 degrees, and the calculations are available here. Each axis has its own calculation. For example, on our C1 axis, we used a 1 to 2 reduction and a different result came out. On C2, we used a 1 to 10 reduction and a different result came out. So each axis has calculations for both rotary and linear modes. For example, our x-axis is a linear axis. We use a 1:5 ratio ball screw system. A different number has emerged. We have a formula to calculate this. We use that formula. When we directly write the number that comes from that formula here, our machine will operate with the correct stepping. And on the machine, we have this feature. When we turn it on, we have a sensor right here. The machine mechanically detects this sensor. After we've seen it, we need to write a number for its 90-degree flatness. There is a concept that we call home display. How exactly do we determine this? We do this through a comparator. That is, we set up a brand new comparator. With that comparator, we determine how much we actually need, like 1 millimeter, 2 millimeters, 3 millimeters, or even 10 millimeters. Here on our settings page, we have a home display section that's available for each and every axis. Here, this varies for each axis on the home displays. Our X2 axis, for example, showed a number like this. We determine these entirely by using a comparator. Now, our machine has a tool change magazine system. We will show you how to adjust this. Before adjusting this, it's crucial to send the machine to its home position. All machine positions must be 0 for our adjustments to be correct. We home the machine. Our machine is now ready. Now, this is what's going on. I'm lowering the machine's speed setting for our machine as tool number 1, which we refer to as tool 11 in our tool change system. It's our primary tool. I'm instructing it to select tool number 11. Now, because our machine isn't set up, we need to be careful. When it gets to this point, I stop it. I stop it right here because I need to adjust everything that comes after this. How do we go about setting up our tool change right here? First, by lowering the Z-axis down from the main axis. We're lowering our Z-axis now. There's a specific slot for each and every team there. For our tool to reach the correct position, we must locate the exact center point here. This requires making plus-minus adjustments on our C1 axis and simultaneously on the X-axis, the X1 axis, and the C1 axis. This means the tool needs to enter precisely at the center point. We perform these adjustments manually, just like this. There are specific methods to check this. For example, once you've placed the tool inside, you observe the motor's ease of rotation. If the motor shaft is turning freely, that means no problem. It's lagging right now. For example, the mechanics are stuck inside. What do you need to do? This time around, you need to intervene from here. So when you make small, gentle interventions from the C1 axis, look now. Our machine is currently moving along the correct axis. Now, once we have successfully located the correct axis, the crucial and important step we must take here is this. To adjust the value of the C1 number and also the X1 value within the settings section. We have a tool section from here, which axis would number did we set? We set it to number 11. Look, number 11 has a C section here. We write the value from C1 here. Here, we also have an X section. And into this, we enter the value from X. Then we also have our Z section. The Z section can vary depending on the specific mechanics we've implemented. This determines the maximum set level the machine will descend to when changing tools. And we can observe this again when we manually lower the machine. Here, for each tool, due to our circular tool changing system, we are able to calculate it completely over 360 degrees. This means that when we adjust the first tool by adding 36 degrees and then another 36 degrees to the others, we are able to directly input all the values from this point. But if you're using a simple tool change, here with the same logic, if you know the X and Y values, you can adjust the other tools in the same way without much effort. Our tool data is as follows. When this machine software was being developed, we spoke with Mr. Shahin then. From number 11 to number 19, it uses what we call the spindle tool change section. Following that, number 2, number 3, number 4, and number 5. This can be extended. It can go up to 8, 9, or 10. These are what we refer to as auxiliary axes, meaning we can use them as C axes. Plus, we can install what we call a cool laser system. We can add different pens, different pistons. We can completely duplicate these. However, the section from 11 to 19 is solely for the spindle. This part is exclusively for the spindle. Now in our settings, for example, in the tools section, there's something like this. What we refer to as team change velocity is the speed at which we switch between teams. This means we can either reduce or increase it as we wish. From this point, it can display which team is currently active at the moment, and from here we are able to toggle it on or off. And this, for example, are the waiting times when changing tools, such as the valves opening time or the covers opening time. We are noting down these durations. We have a section here, and this is where we list all the tool numbers the machine will use. Every tool used by the machine must be entered here. When we refer to displace, this also covers safe distances, meaning during tool changes. After getting the kit, it needs to reach a certain Z safety distance. We write this here. And we have our tool zeroing sensor. This is the tool zeroing sensor that you can see right here. For this sensor, we also provide speed and coordinate information in the very same way. That is because it's located on the x-axis, and since it's a straight axis, we only provide it as the x-axis. When we provide the coordinates, our machine can automatically perform tool changes. And by the way, also for the other tools, right here, just as we do for T11 and T12, we are noting down the differences between the tools. What I mean is between the spindle and our second tool, which is C2, there is a certain difference. For instance, there might be a difference of 10 or 20 millimeters. We are documenting these central coordinates right here. Our designated reference team, which is essentially our flagship team, is typically T11. T11 invariably functions as the absolute center, the foundational 0 point. All other teams establish their central point by taking T11 as their primary reference. You saw that, didn't you? Right over here, for example. We are writing down the T3X distance measurement.
There's only this much distance between Z, C.
For example, it uses 3 axes with this. Now from here, the tool change system that we call type means you're specifying which axis it uses when performing a tool change. So these are C, X, Z, which our machine is currently utilizing. You previously had a flat tool changing system. Here you could also use Y, for example. You can use Y instead of C, and you're able to change this from here as well. For example, you can write it as XYZ or CYZ. You can completely change it based on the mechanics you've implemented. Right now on our machine, we're going to implement the tool change system, and following that, we will adjust the height settings for the tools. Tool T11 is currently active in our machine spindle. We are instructing the machine to retrieve tool T16. The machine first moves to release the tool it currently holds in its spindle, which is T11.
Then we need to get the T16.
Now that we've connected a new tool, we need to register its height. Right here, you'll find a button. The moment we press this button, the currently active tool will automatically go and retrieve its height data. we've received the tilt information for our tool. Now our machine has a system we call reference, which is a position which automatically provides the Z height. For this, we need to perform an adjustment. Our TU11 tool must be selected from here. Our designated reference tool is always TU11. Manually, and then we attach a ring to the machine. We accurately input the outer diameter of this ring onto our screen. After that, we manually lower the Z1 axis.
We can increase or decrease our speed from here.
When I'm getting closer, we begin to slow it down slightly. Busy here, so and when it reaches the point of touching our bracelet like this, from the reference section here, from our reference section, the moment we click the Z1 button, our machine completely retrieves the reference information. And right now, our reader sensor also goes to get its own reference based on this. So automatically, the reader sensor is now going to get its own reference at the Well, if we prevent this operation, our sensor won't give accurate readings.
So we shouldn't stop it, it needs to go on. Over there.
All right, so for our machine, the T11 spindle is our primary reference tool. This means that all of our centers are established and measured according to T11. Now, after we've set our T11 exactly to the center of our collar, meaning the reducer here, so that other tools also align correctly. For example, when we select T2 from here, for T2 to also be able to come to the center point in the same way in the settings section here, we have a setting in the tools. Specifically, there's an X value here. The purpose of this X value is that once we accurately input the distance between T1, T11 and T2, all tools will then move to the correct position, the correct tool zeroing point and the correct working point according to this reference tool. And the centers for our reading sensor, which we refer to as a scanner, are located right here. In our settings within the system, there's a scanner section. We need to enter the axis it's on. For example, ours is on the Z3 axis. We must specify which axis it's on. From here we can activate or deactivate it. Here we enter the necessary waiting times for its operation, and here we input what we call the X center, where our scanner will go, meaning the X and Z center coordinates for it to move to the exact correct point. This is also the operating speed. That's all. We are currently in the electronic section of our machine. We have a single main board here. Our main board is a 4-axis system. It consists of the X, Y, Z and C axis. And here we have, with these multiplier cables, we can multiply the axes like 3 C axis and 4 Z axis. Through these cards, we also enable direct communication with the servos. So this card ensures communication between the main board and the auxiliary board. These cables in turn provide communication with the servo. Here you'll find the input and output connections for our card. Each input and output has its own corresponding number, as we're showing you on the screen. These sections here are for input, specifically for sensor connections, and these other areas are for output, where we provide connections for components like valves, relays, spindles and drivers. This is the section of our lasers that we call the reader scanner. Here we have our relays. The commands coming from the output go directly to the relay, and then through the relay these commands are sent to the driver or the valve wherever they need to go. For instance, if the X1 axis needs to operate, a specific command is sent from the output on our main card directly to the relay. The relay then sends this command directly to the card. Now,
This section is also about the time we choose our model.
Out.
Once they're here, we select the tool to be used, the one on the machine. Here's our working speed, the machine's operating speed during machining. If we use analog output from our system, we can enter the spindle speed here. If we're using the analog output on the board, so this thing we refer to as dot step takes our regular line and converts it into points. For it to be able to perform this operation, the model itself must inherently be a standard line. This thing that we refer to as width here, it actually defines the overall width of our model. So right here on the main display, we have a specific width setting. This particular setting determines the bracelet's width, which is essentially that red line you see. And the one located here, it sets the model's width within the boundaries of that very red line. When you refer to weight offset, it's...
If we want, our model can go right or left.
We are able to carry it. The height is directly 360 degrees, meaning it's a circular rotation. Because we're working on bracelets, it's a 360 degree circular turn. If we were to change this, what happened completely? Our model's incomplete, but if we delete this and hit enter, it restores its original. When we refer to height offset, we're talking about what we call the starting point, meaning the initial point on the collar, which we can adjust if desired. We have the ability to initiate this starting point from a different position. On the collar, where we define depth, there's a specific diameter that we've indicated here. In addition to this diameter, we also specify the exact depth of processing that the collar needs to perform. When we refer to the depth step just below, it means the number 4 we wrote here should be done in 1/10 increments, meaning 4 times. If we write 2 here or 0.2, then it will be done 2 times, like dividing the top number by the bottom number. Now, since the tool we have selected is the C-axis, the C-axis features open up here. The C-axis has 3 distinct features. The fixed mode, which is a stabilization mode, means it remains fixed at a specific angle. At that angle, it projects a model. The tangent mode draws a pattern by following the X and Y path, meaning the X and Y lines perpendicularly. When we say free, it's used for a complete 360 degree free rotation. These are only C-axis modes. If you select the C-axis from the tool here, it will open. Look, the moment we select T4, this already closes. Because T4 is a normal tool, it doesn't use C-axis features. Over here we have an X reference section. This is our X2, our specifically angled arm. If you're planning to create an angled bracelet or execute any kind of angled operation, the instant you input the precise angle right here, the machine, immediately before it commences processing, will first securely fix the arm according to that exact angle. It comes into play at a later stage and it performs its operation in that specific manner. Currently on our machine, we have our X1 reference point available. This is for adjusting our tools to ensure they arrive precisely at the very central point of the bearing. In this way, we go directly to the exact center point. Then, following that, there is a Z1 reference. This also makes sure that when we enter the diameter in a circular fashion, it will land on the correct spot. It is also necessary for this particular setting to be made. And then, after that, there is an X4 reference. This is our setting, for example, when we change the 20 millimeters we've entered here to 15 millimeters. X4 ensures the machine is correctly positioned. Z4 ensures the machine's... When we adjust the diameter and radius here, for it to reach the correct point, that is, if our bracelet is 24 radius, when we input 24, for it to come to the precise spot, all of these require a one-time calibration. Some fine-tuning and adjustments need to be made. So for today, we've tried to convey all our general information regarding our machine. See you in our next video.